Let's check this one out. Pulley problem. Okay, so we got a pulley. Let's do this. Remember, pulley problems, also known as Atwood's machines. If we, let's add some masses here. Put a mass here of, I don't know, 21 kilograms on this side. And let's go with, well, let's do an unknown mass. This has some unknown mass in it. Ooh, unknown mass. But let's say that it is at least heavier. It's heavier. And let's say that the system is accelerating at, I don't know, 2.4 meters per second squared. Okay. What we'd like to know is what's the mass of the other block, and if we could find it, if it'd be nice, what is the tension in the rope. Okay. If we want to set up a problem like this for this Atwood's machine, the first thing we really need to do, the first thing we need to concern ourselves with is drawing a free body diagram. Okay, so if we're drawing a free body diagram here, this is one block, this is the other, and what we really care about here is that the green block, it has a weight mg, we'll call this weight 1 for mass 1, and since we actually know what the first mass is, 21 kilograms, we can just say that this is the quantity 21 times 9.8. Bust out the trusty calc. 21 times 9.8, 205.8. Let's just round it up for simplicity to 206 newtons. Okay. We can't forget that there is also a tension acting in this rope. It's going equal and opposite. That's why the rope doesn't move within itself. So there's a tension going on here. Vertical tension. On the flip side of things, with our red mass, it has a weight acting down. That weight, once again, equals mass times gravity, but we don't know what the second object's mass is, so that's fine. We'll just deal with that. And vertically, there's a tension. Okay, so that's what's going on there for our free body diagrams. So for our free body diagrams, we just have weights on each of them. We have tensions acting up. The only thing we need to do from this point is we need to choose what is a positive or a negative direction. In terms of what we could choose as a positive negative direction, it doesn't really matter as long as you choose something. What I like to do in a problem like this is, since I know that this is the heavier mass, just because I told it to you, I like to note that this one is falling while this one is rising, and that means it's going across like this. So I'm going to pick the direction of motion as positive. Now, if I didn't tell you that was the heavier mass, it wouldn't matter what direction you picked as positive. Like, we don't have to pick this direction as positive right now. It doesn't matter at all, as long as you keep your convention. I just like to choose the direction of motion to be positive, because if I choose this motion as positive, that means the acceleration will stay positive. If I flipped this direction of motion, or if I flipped my convention so that the other way was positive, then the acceleration is technically negative because this block may still be going down. Okay, so just a little thing there. That's just how I like to pick directions of motion. So because of this, because going up for the left block is the direction of motion, the positive direction, we can call that plus and minus, and then because the tensions have to be equal and opposite, that becomes minus plus. And with that, that's basically all of the intense physics we had to do. At this point, it's just writing out the same old equation every time. F equals ma. We wrote that in calligraphy because it's cool. But if we write out F equals ma here, when I'm looking at my left diagram, I see I have two forces, because remember, this is technically the net forces. It's all the forces acting. So our two forces we have here, we have a positive tension. I mean, we wrote T tension and we said it was positive, so for the F net, there's T for tension. We also have a weight. It's negative, so minus weight of the first one, so W1, equals the mass of the first one times A. For our second block, in this case, our weight is actually positive and our tension's negative, so we can say weight 2 minus tension equals M2A. So right there, we set everything up. That's the physics of this. Physics is all done. Don't have anywhere to go here, but to the world of math. So if we would actually like to go about and solve this problem, we can start doing that with these equations. What we can begin to set up is, because we know what the weight is for this first object, we can take that weight and we could plug it in to the equation. So what we can do here is we can say that for this equation number 1, we can say that the tension minus 206, because that was the weight we found, equals M1, which was 21 kilograms. So we can just drop in a 21 right here, times the acceleration. And the acceleration we have from before is 2.4 meters per second squared. And that acceleration is positive because our object's moving up here. So we can just say 21 times 2.4. Now to solve for t, if we look at this equation, we can see that, hey, we have every other number or variable other than the t, so we can solve for it. If we just move 206 onto the other side, what we'll have is t equals, well, whatever 21 times 2.4 is. Busting this out, I got 50. Rounded, of course. So 50 plus 206 equals T, so that's 256 newtons. That's the tension. Okay? So that's what we were looking for, one of the parts here. That's nice. What we can do with this tension, though, is for our second equation, we can plug it in there. Because we know this tension, we can take it and dump it over. This is kind of our putback. So what we can say for our second equation is we can say that the weight of the second box minus 206 equals the mass of the second box, which we don't know, totally unknown to us, times a known acceleration of 2.4, because both of these objects are going to have the same acceleration. It's a rigid system, they're going to be moving together. What we need to remember here deals with this weight. We need to remember that weight equals mg. We wrote it in our picture. We wrote it right here. But let's just sub it in. Because when we do that, when we say the mass of the second block times g, 9.8, minus 206 equals m2 times 2.4, we see that this mg and this m2.4, those are like terms. Both are a mass multiplied by an acceleration. So what we can do here is we can add the 9.8 times the mass to each side. Remember, even though the m's coming before the 9.8, you can flip them. It's just where you'd like to place your variable. And if we do that, oops, we're actually subtracting. I'm sorry, I made a boo-boo. We're subtracting here, kids. We're subtracting 9.8 from each side. That's actually a nice thing, and I noticed that error because what we're going to have in a second is negative 206 equals 2.4 minus 9.8 equals negative 7.4 m2. I noticed that I made an error though when I said to add, because my mass shouldn't be a negative number. I need a negative on each side because these negatives are going to divide out. Now, when I divide each side by 7.4, I find that 206 divided by 7.4 equals 27.8. So what I end up finding for M2 is that it is 206 divided by 7.4, or 27.8 kilograms, give or take, depending on how you rounded throughout the problem. Okay, so that's what we're doing here. I knew it had to be a positive number because of that. Everything from that box, that was just math. Okay, the things I am most concerned with you setting up tomorrow, and anytime you're doing a problem, is this equation right here and this equation right here. These are our two important equations. If you can get those, you're golden. Okay, you're golden, pony boy. That's what we're looking for. But in the end, we have an Atwood's machine, a pulley problem. We're looking for mass and tension. Free body diagram. F equals ma. Plug in some numbers, and then from there, play with the math. Okay? And with that, this problem is finished.